Let us continue with another examples on the ACL. For example 5, we are given these problems here. We have a current filament on the z-axis, which carries a current of 7 milliampere in the positive z direction, and current sheets of 0.5 ampere per meter in the z direction, positive, and negative 0.2 z direction, located at r equals to 1 and r equals to 0.5 cm respectively. So based on this given configuration of current, we need to calculate the magnetic field intensity at these three locations, three radius, which is at 0.4 centimeter, 1.5 centimeter, and 4 centimeter. Okay, and then for the fourth question is what current sheet should be located at r equals to 4 centimeter so that h will be 0 for all for all the radius of r which is bigger than 4 centimeter. So let us do it one by one. Let us sketch the problem first. We are having 7 milliampere filament current on the z axis, and then we have two current sheet, 0.2 of negative z at 0.5 and 0.5 of z at 1 centimeter radius. So let's have a look at this configuration. Let's sketch it together. So we have the first one is at the z direction, z axis. In positive z axis, we have the current having 7 milliampere. 7 milliampere magnitude. Okay, and then we have the first surface current located at 0.5. Okay, so that should be 0.5 radius. Okay, so this is 0.5 radius, r equals to 0.5 centimeter radius. So for that radius, we have a current of 0.2 of negative z direction. Okay, so that should be surface current, basically, right? So we have GS equals to 0.2 of negative z direction. Okay, and then we have a next, it will be the next surface current. I'm using green color for that. All right, so that should be our next surface current, in which the radius of that is 1 centimeter. Okay, so r equals to 1 centimeter, in which the surface current to that particular surface, GS, is equals to 0.5 in the z direction. So we have 0.5 in the z direction, ampere per meter units. Okay, so these are the configuration for the current distribution that we have. We have one filament, and we have two surface current located at different radius at 0.5 cm and 1 cm. So based on this, you need to find out the H field intensity at 0.4, 1.5, and r equals to 4 centimeter. Okay, so we have, let us write here. So r equals to 0.4. Okay, and then we have r equals to 1.5 centimeter. And number 3, we have r equals to 4 centimeter. So these are three locations of radius that we need to configure. We need to obtain the H field intensity. So let us do it one by one. Okay, so if we base on this, we have, let's say for the first case, r equals to 0.4. So for this, we are dealing with the region of r less than 0.5. So r less than 0.5 centimeter. That should be our interest now. And if we can sketch the Ampere loop, Ampere loop for this region, let us use a blue color for this. So that should be our region of interest, which is for r less than 0.5. So again, our loop is a circular structure. Okay, so if we base on the ACL, we have H dot dl equals to the I enclosed. Okay, so the H dot dl is the integration on the loop. On the loop. So if we integrate it, we are supposed to get HV of 2 pi r. Because we know that the dl is r dv direction of v. So this is a typical the value for the H dot dl, which will give us a result of the integration of the closed loop will be HV of 2 pi r, and the I enclosed is the current enclosed by the loop, which will be the 7 milliamperes current. Yeah, 7 milliamperes current. And if we proceed further, we are going to get the HV, okay, will be equal to 7 times 10 power of negative 3 divided by 2 pi r. And as such, we are going to have H vector should be 7 times 10 power of negative 3 over 2 pi r, okay, direction of V. And for this, we can straight away calculate the H field for R equal to 0.4, because 0.4 is less than 0.5 cm. So for that, we can say that for R equals to 0.4 centimeter, so your H field will be equals to 7 times 10 power of negative 3 divided by 2 pi of R, which is 0.4 times 10 of negative 2 in a free direction in ampere per meter unit. So that should be your H field intensity at R equals to 0.4 centimeter. Okay, so for the second region, for the second case, whereby we have the radius of R equals to 1.5 centimeter. So if you look carefully, this is the region of our region of interest will be R bigger than 1 centimeter. Yeah, so that should be our region of interest. Because the radius here is 1.5. So based on this diagram, our region of interest is for the region which is having a radius of R bigger than 1 centimeter. So as usual, let us catch the Amperian loop for this region. So that should be our Amperian loop. Yeah, that should be our loop for the second case. Yeah, in which if we base on this, we can write that the ACL, H dot dl will be equals to I enclosed. For left-hand side, we are supposed to get HV of 2 pi r, whereas for the I enclosed, we are supposed to get 3 current distribution. Yeah, the first one is a filament of 7 milliampere. Then we have a surface current at 0.5 cm, and following this, we have a surface current at 1 centimeter. So the I enclosed will then consist of 7 milliampere, yeah, as a filament, plus a current current amount at 0.5 centimeter. So that we're going to have need to have a subtraction then, because the current is having a negative z direction. So we have to subtract with a 0.2, which is a surface current density, yeah, and multiply with the radius with the parameters of the 0.5 cm radius, which is 2 pi of r. Yeah, r is 0.5 times 10 power of negative 2. Okay, and we need to add further with the current located at 1 cm radius, which will be 0.5 z, 0.5. 0.5 multiplied with the parameters, which is 2 pi times 1 cm. Yeah, so that should be the enclosed current. Yeah, enclosed current. Okay, and following this, we can have that the HV will be equals to 7 times 10 power negative 3 minus 0.4 pi. 0.4 pi times 0.5 times 10 power of negative 2 plus pi 1 times 10 of negative 2. And all of this should be then divided by 2 pi r. Okay. And for this, we can have that the H vector shall be equals to HV direction of V in ampere per meter. So what we have obtained here is the value of H field intensity for region of R, radius of R bigger than 1 centimeter, in which we can find the H field at 1.5 simply by substituting R as 1.5 cm. So for that, we can write that at R equals to 1.5 centimeter, so your H vector will be equals to 7 times 10 of negative 3 minus 0.4 pi multiplied with 0.5 times 10 of negative 2. Okay, sorry for this. Okay, and then we need to add with pi of 1 times 10 of negative 2, and this will be further divided by 2 pi, and r should be then substituted by 1.5 cm times 10 of negative 2. So that should be the HV, yeah, in the phi direction in ampere per meter unit for a position or the radius of r of 1.5 centimeter. Yeah, so please solve the values, the numerical values for this H field intensity. Yeah. Okay, and for the third problem, which is at 4 centimeter. So I think that for the third one, it is similar to the second one, in which 4 centimeter is located outside 1 centimeter radius cylindrical structure. So basically for the third one, simply we shall use a similar H field intensity terms, okay, but we need to substitute R as 4 centimeter then. So for values of R equals to 1 equals to 4 centimeter, we can use a similar equation, but need to change the value of R to be 4 centimeter. So that will be 4 times 10 of negative 2. So that should be the H field intensity at R equals to 4 centimeter. Okay, right. And part D is what current shape should be located at R equals to 4 cm so that H will be 0 for all R bigger than 4 centimeter. Okay, so for this particular case, the question asks us, need to erase this one first, sorry, yeah? Sorry. Okay, we have, okay, this is your filament current. Okay, this is your cylindrical structure having this first JS, and then we have the second JS. Yeah, right. So the question is that we are given that supposedly there is an additional structure drawn at R equals to 4 centimeter. Sorry, not that nice, my drawing. Yeah, this is at 4 centimeter radius. All right. So this is 4 centimeter. Okay. So the question is, if there is additional sheet at 4 centimeter, what should be the density of this current? What should be the JS values at this 4 centimeter radius, so that H will be 0 for all region, all radius of R bigger than 4 centimeter. Okay, so this is quite straightforward questions basically. I shall refer to these questions. I mean this part here. Okay, let me erase. Okay. Given the questions then, we need to see that the region of interest will be R bigger than 4 centimeter. Yeah, so that should be our region of interest. And if we base on this, we can write the ECL should be equal to these terms then. Yeah, and the question is what should be the current that should be located here at 4 centimeter radius. So for that, what we can say is that this will be our the loop, the Ampere loop for the radius of R bigger than 4 centimeter. Okay, and for this we can write that for left hand side, which is the integration in the loop, I'm going to have it as HV of 2 pi of R, while the enclosed charge now will consist of 4 charge distribution. Current distribution. We have a filament at z-axis. We have 0.5 0.2 ampere per meter at 0.5 cm. We have 0.5 ampere per meter at 1 cm, and additionally we have GS at 4 centimeter. So that's our concern. What should be the values of GS that need to be added then? So basically, we can calculate the GS by simply include it in the I enclosed. So now the I enclosed will consist of 4 different terms. We have J 7 times 10 of negative 3. Okay, minus 0.2. Okay, I can just put it as 0.4. 0.4, okay, pi, and then we have 0.5 times 10 power of negative 2 plus pi 1 times 10 of negative 2 plus for the 4 centimeter radius we have a GS which is unknown multiplied with 4 times 10 of negative 2. Okay, so then we have 4 enclosed current terms then. Okay, so for this, when we proceed with these left-hand side and right-hand side terms, we are supposed to get H field shall be equal to 7 times 10 power of negative 3, yeah, minus 0.4 pi, 0.5 times 10 of negative 2, plus pi 1 times 10 of negative 2 plus GS multiplied with 2 pi r supposedly. So that should be 2 pi then. So we have 8 pi, okay, times 10 power of negative 2. Okay, so from here, we are given that the h will be 0, yeah? So when we equate the left-hand side to be 0 then, so by right, we have the only unknown is JS. Yeah, the only unknown in this equation will be the JS. So from here, I believe that you can figure out what should be the JS value based on this solution of this equation. Yeah, so from here, you must be able to find out what should be the JS magnitude that shall be included at 4 centimeter radius so that the H field intensity will be 0 for all region bigger than 4 centimeter. Yeah, okay. Right, so let's have a look at example number 6. We are given these problems whereby there are 2 wire transmission line. The cross section is illustrated in this figure below. Each wire is of radius of 2 centimeter and the wires are separated by 10 centimeter. The wire centered at 0 point carries current of 5 ampere in the direction of positive Z, while the other one, which is centered at 10 centimeter 0, carries the return current. So find the H field intensity at 5 centimeter 0 and 10 centimeter 5 centimeter. Okay, so let's find out the H field first at 5 centimeter 0, which is basically located at this center between these two currents. So the first current is 5 ampere in a positive Z direction. So if based on this diagram, we have X direction. This is the Y direction. So Z should be in this direction supposedly. Okay, so we can see that the current is in a positive Z direction. So this will be the current direction. Yeah, the positive Z. We have 5 amperes, whereas at 10 centimeter 0, it carries return current. So we have the current is flowing towards the negative Z direction. And again, the magnitude should be the same, it's 5 ampere, but the direction is towards negative Z. Yeah. Okay, so based on this, need to find out what should be the current, what should be the H field at 5 cm0, which is located here, right? So if we base on this diagram, we know that the H field intensity, yeah, should be contributed by two current then. So we have H1 and H2, in which we assume that H1 is due to the 5 ampere current flowing in the positive direction, whereas the H2 is the H field intensity produced by the 5 ampere current but flowing in the negative Z direction. Yeah. So H1 is due to this current and H2 is due to this current. So let us find out the H1 and H2. So for the H1, okay, knowing that your current, your transmission line is infinite in length, because we are not given any information regarding the length of this transmission line. So we can assume that the length is infinite. So the H1 will be equals to I divided by 2 pi r in the phi direction. Okay, in which I is 5 ampere. Yeah, and then we have 2 pi of r. Yeah, So R is what? R is your radial distance. Sorry, yeah. R is your radial distance from, sorry. So we have 2 pi R here. Okay, so then we have 2 pi. So R is a perpendicular distance from the filament, yeah, to your point of interest. So based on this, we can see that the R should be equal to 5 centimeter. Okay, so 5 centimeter. Okay, and the phi direction should be now changed into L cross R, supposedly. Okay, so what should be the L direction? Which is the current direction. So the current direction should be in a positive Z direction, whereas the R should be in this direction. Okay, so R should be in a positive X direction. Yeah, so it should be Z cross X. So end up we're going to have the H1 should be 5 divided by 10 pi, yeah, times 10 power of negative 2. The Z cross X will give us Y direction. So this is the H1 in the ampere per meter unit. Okay, whereas for the H2, yeah, contribution by this 5 ampere flowing through negative Z direction. So the H2 will be I over 2 pi R, direction of phi, okay, and R is 5 ampere. Okay, 2 pi of R is a perpendicular distance. So again, the distance is 5 centimeter. So we have 5 times 10 power of negative 2. And the phi direction should be now substituted as the current cross the R, L cross R. So L will be negative Z direction and R is in this direction. So R is negative X. Yeah, R is negative X direction. So when we proceed with the solution, we're going to have the answer will be 5 over 10 pi times 10 power of negative 2. So negative Z cross negative X will give us positive Y direction in ampere per meter. So from here, when we add the two, H1 and H2, we are supposed to get the answer to be 1 over pi times 10 power of negative 2 in the Y direction in ampere per meter unit. Okay, so that should be your H field intensity at the point of 5 centimeter 0 contributed or produced by these two transmission lines. Yeah. Okay then. And then we need to find out for the second case, which is H field intensity at 10 centimeter, 5 centimeter. Okay. Right. So again, let us resketch the position of the current. So this is 5 ampere towards positive Z. This is 5 ampere towards negative Z. Okay. So the point of interest now is at 10 centimeter, 5 centimeter. Supposedly that should be the point here. Yeah. This is 10 cm, 5 cm, the position. And we need to find out the H field at this position then. So again, we need to, we can say that the H field will be contributed by these two current. So we are supposed to get H field will be H1 plus the H2. Okay, H1 is contributed by 5 ampere current here, and H2 is contributed by 5 ampere current here. Okay, so let us find the H1 first. So H1 will be again equals to I over 2 pi R in the phi in the vector direction. Okay, I is 5 ampere. We have 2 pi, and R is a perpendicular distance from the filament to this point of interest. So your R should be equal to this R, yeah. Sorry then. Okay. Okay, so your R should be this perpendicular distance. Sorry, not that straight my line. Okay, that should be the case, yeah. All right. That should be my R, yeah? That should be my perpendicular distance. So basically from here, we can see that this is 10 centimeter, this is 5 centimeter. So R basically will equals to set of 10 cm, or we can say that 10 squared plus 5 squared square root. Yeah, so that should be square root of 125. Okay, so that should be the value of R. Okay, 125. So we can have it as a square root of 125. Okay, and then for the phi in the vector, again, that should be the L cross the R. Okay, and if you proceed with the H1, we're going to have a 5 over 2 pi instead of 1 to 5. So you need to convert this into meter unit. Yeah. So L will be in a positive Z direction, whereas for the R, if you base on this diagram, you can see that the R in the vector should be equals to 10 direction of X, okay, plus 5 direction of Y divided by set of 1 to 5. Yeah? So that should give us 10 direction of X, okay, plus 5 direction of Y divided by set of 1 to 5. Okay, and if you proceed further, we're going to have H1 will give us 5 divided by 250 pi. Okay, and then we're going to have a Z cross X will give us Y, so that will be 10 direction of Y, and Z cross Y will give us negative X, so then we're going to have 5 plus 5 direction of negative X. Okay, so that should be the case. That should be our H1. Yeah, that we're going to get contribution of H field due to the first current of 5 ampere directed towards positive Z. Okay, and for the H2, yeah, for the H2, which is due to the 5 ampere here, right? So we can write that the H2, okay, the H2 will be equals to again I over 2 pi R direction of P. Okay, so I is 5 ampere, so we have 2 pi. So R is a distance from this line to the point of 10 centimeter, 5 centimeter. So R should be equals to 5 centimeter, basically. Okay, 5 centimeter. And for this phi, you're going to have the L will be in negative Z direction, while the R should be in a positive Y direction, yeah, because R is in this direction. Okay, so R in positive Y direction. And following this, you can say that the H2 will be 5 over 10 pi times 10 of negative 2. Okay, and Z cross Y will give us negative X. And because we have negative sign here, it should be then positive X direction. Okay, so that should be our H2 contributed by 5 ampere current number 2. So then to find the total current, total H field at 10 centimeter, 5 centimeter, we just need to add H1, which has been obtained earlier with the H2 that we have recently obtained. Yeah, so that should be your H field vector at the point of 10 centimeter, 5 centimeter. Right, so that's the end of lecture 16. So following this, we're going to proceed to lecture 17, in which the topics covered will be on the Stokes theorem, magnetic flux density, and then we're going to summarize the Maxwell's equation for the static field condition.